Hello, vanakkam, salam, namaskara. Welcome back to Next Gen Actors Academy. Yes, today we are having an important concept called Slater's rule. This is bit confusing for many students. They feel it is confusing, but it is no longer confusing story now onwards because you are going to get the clarity today. Yes, what is Slater's rule? Yes, I have seen, but the information about Slater's rule is very limited in the net. So that's why I thought of what making this. What is Slater's rule is simple. Slater's rule is what? It is the effective nuclear charge. It is the tool to calculate the effective nuclear charge, the net attractions experienced by outermost electron from the nucleus. Yes, what is that? Let us see. For example, you take an atom. If this is the nucleus of atom, and just imagine there are energy levels. Here, just imagine one electron here. Yes, see, for example, let us say sodium atom. If you take sodium atom, what is there? 11 protons will be there in that. So just imagine 11 protons are there inside. So first shell, second shell, third shell. If you write the electronic configuration, 1s2, 2s2, 2p, 6, 3s1. There are three shells, first, second and third shell. The valency electron, this is called valency electron. The valency electron is expected to have 11 protons attraction. This is expectation. Reality is different. Why? This electron, when there is no inner electrons between outer electron and nucleus, we are expecting 11 protons attraction. But in reality, when there are inner electrons in between nucleus and outermost electron, definitely there is a decrease in effective nuclear charge. What is that? See, when there are no inner electrons between nucleus and outermost electron, we are expecting 11 protons attraction on this outermost electron, valence electron. But when inner electrons are coming in between outer electron and nucleus, in the process of revolving around the nucleus, these inner electrons are what? Negatively charged. They repel outer electrons from the nucleus. Obviously, they experience less attraction. This outer electron experiences less attractions from the nucleus. The decrease in the nuclear charge, the decreased attractions is nothing but what? Effective nuclear charge. That decreased attraction is because of what? Inner electrons. Clear, right? Yes. What is effective nuclear charge? The net attractions experienced by the outer electron from the nucleus. Why effective nuclear charge is less than the atomic number or expected nuclear charge? Look at this. When there are no inner electrons, this outer electron is expected to have 11 protons attraction. But in the process of revolving, inner electrons are coming in between outer electron and nucleus, and they are repelling. They are pushing electron away from the nucleus. That's why this electron is experiencing less attractions, less than 11 protons attraction. That decreased attraction will affect the size of the atom, electronegativity, ionization potential, everything is linked with that. That's why try to understand this. This centripetal force, we say, this is what electron repulsion. So centrifugal force we say, otherwise centrifugal work force also we say, balancing force. So centrifugal force is what? The classical physics old method, but quantum mechanics says electron repulsion in simple way. Clear, right? Yes, this electron repulsion is responsible for what? Keeping this electron away from the nucleus. Nuclear pool, opposite charges will have attraction. That is what? Responsible for keeping electrons within the atom. And why the electrons are not colliding with the nucleus? Because electron repulsion, interelectronic repulsion we say. Yes. So now when there are no inner electrons, we expected 11 protons, but inner electrons are there here. Then what is the net attraction forces experienced by the outer electron? Can be calculated with the Slater's rule. That is the beauty of Slater's rule. What is Slater's rule? Let us see. He has given one formula: effective nuclear charge. Z effective means effective nuclear charge. That is what atomic number, right? Is equals to atomic number minus sigma, even we write as S. S is what? Constant. This is a constant. Clear, right? So this constant value, by using Slater's rule, we calculate it. Clear, right? And this is what? Atomic number. For example, sodium is there. What is the atomic number? It is 11. and we calculate what? Screening constant value by using Slater's rule for sodium valence electron. That value we subtract from 11, then whatever you get it, that is what? Effective nuclear charge. So whatever the value you get it here is what? Less than the 11. Why it is decreased? Because these inner electrons are working as a shield or a screen, protecting layer kind of. So that's why outer electron experiencing less attractions. Clear, right? Yes. Without wasting time, we go to the next topic. Look at this, the slide. Here, Slater's rule, see the effective nuclear charge we can calculate it by using Slater's rule. So, what is Slater's rule? And this we will calculate it especially as what we need to do is we need to group the electrons actually. So, what is meant by grouping? Let us see. See, for example, normally, okay, what is our rule? 1s to 2s to 2p6, 3s to 3p6, 4s to 3d10. Like that, we write increasing order of energy, right? That is our rule. So here, this Slater's rule says that there are certain energy levels around the nucleus, and orbitals, electrons present in an orbital, are what grouped in such a way that look at this: 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, like that. Okay. So here, this is one group. 2s, 2p, you make it another group. 3s, 3p, you make it other group. 3d other group. 4s other group. 4p other group. So 4d kind of what? Different groups we have divided. So grouping we say. So energy different levels kind of. So one after other, one after other. Why we have what we have separated like this is simple. Try to understand one particular concept. For example, S electron. What is the orientation of S electron? How S electron is oriented around the nucleus? Let us see this. See, S electron probability is what? Close to the nucleus, right? In a circular area orbital, the S electron is available. Am I right or wrong? Yes. So that means S electron is always available around the nucleus, spherical shape. Clear, right? So S electrons are always, S or P electrons, generally they are close to the nucleus. Their probability to find electron will be very next to the nucleus, close to the nucleus. That's why whenever something is there near to that, it can protect. So for example, outer electron is there. See, for example, just imagine here one outer electron is there. So this electron is spherical in shape. This availability is next to the nucleus, very concentrated around the nucleus. That's why it can protect electron effectively, either here or here or here, even upward or downward. So 360 degrees, that S electron can protect outer electron from the nuclear attraction. That's why protecting power will be more for S electron. Even P electron also. P electron is little less diffused so than D and F, but like S electron only, P electron also available close to the nucleus. Concentration of P electron is close to the nucleus, right? But D and F, when you take it, D is how? Look at this one D electron I am writing. So D electron is more diffused. Same electron is available in multiple regions. So that means the concentration of D electron around the nucleus is less. Look at this. So if an atom is taken, D electron is more distributed. The concentration of D electron, availability of D electron around the nucleus is less. If it is less, then it cannot protect like this. Clear, right? So, for example, D electron is there here. So the concentration around the nucleus is less. Obviously, it cannot protect outer electron effectively. Clear, right? So that is the reason why. So S and P will have more protecting than D and F electrons. Clear, right? Shielding effect or screening effect order is this. SP will have more screening or shielding capacity than D and F electron. That's why in grouping also what we have done? 1s, 2s, 2p we have done together, and 3s, 3p grouped together. 3d is different. 4s, 4p you can make it 4s, 4p, you can write together. 4d is different. So this is the way you need to group the electrons present in a particular orbital. So energy levels kind of. Clear, right? So come back to this. So by grouping all that, we can calculate it. For example, an electron is present in this last shell. Just imagine it is nth shell. So another electron, whatever is present in the same shell, in the process of revolving, just imagine it is not Bohr orbit. It is not a fixed path, right? This is the region kind of. This is the region kind of. So if inner electron, sorry, if the same shell electron, if it is coming between nucleus, just imagine here nucleus is there. If it is coming between the outer electron and nucleus, then obviously same shell electron also can protect other electron. Yes, so that's why what they have said. So if you are calculating for S or P electrons, same shell electron, whatever the electron present in the same shell can protect, and its screening constant is what, 0.35. And n minus 1 shell, if this is nth shell, this is n minus 1, n minus 2, and this is n minus 3, like that you take it. And n minus 1 shell electron screening constant is what, 0.85. N minus 2, n minus 3 will have 1 only, 0. What screening constant is 1. This is, remember, for S or P electrons. When you are calculating for d electrons, means what? The valence electron is d. You are calculating for d electrons. Screening constant you are calculating for d electrons. That time you need to follow this order. For example, electron present in the same shell like earlier, it is 0.35 only. Screening constant value is 0.35. For n minus 1 electron, n minus 2 or n minus 3, n minus 4, whatever are there inner electrons, their screening constant value is fixed 1. Only one area you have difference. N minus 1 for DF electron, D and F electrons, it is 1. Whereas for S and P electrons, the N minus 1 shell electron screening constant is what? 0.85 for S and P electrons. The reason why it is because S and P electrons, their screening, their availability is very close to the nucleus. Clear, right? So that's why inner electrons, already there, those electrons are very close to the nucleus. N minus 1 electron cannot protect. Clear, right? So obviously the value is different. Clear, right? So only one thing you remember. See, look at this. For S and P electrons, same shell electron protecting capacity is what? 0.35. Our screening constant is what? 0.35. And here even for D and F also, same shell electron screening constant is what? 0.35. But only one exemption is there. That is 1s electron. 1s2 we write it. If you are calculating for screening constant of 1s electron from the other 1s electron, that time instead of 0.35, we need to take 0.3. That one point, remember, we will see the next one. For example, you wanted to calculate screening constant and effective nuclear charge for lithium valency electron. Lithium, how it is, tell me? Atomic number 3, right? 1s2 means first shell 2 electrons are there, 2s1, 1 electron is there. These black colored dots are representing electron. Clear, right? Yes. So effective nuclear charge for lithium, how to calculate it? Z minus screening constant. So you know atomic number of lithium is what? 3, and screening constant we will calculate it now. As I told you, write down the electronic configuration of lithium. What is the electronic configuration? 1s2, 2s1, 2 plus 1, 3 electrons. As I told you, group them. First n, this is nth, and this is what? N minus 1 shell. Clear, right? Yes. So now you are calculating for the last electron. You are calculating for this valency electron. Screening constant for valency electron. How to do that? S is equals to, so one electron is there in the same shell. Other than this, is there any other electrons? There are no other electrons, right? So that's why 0 other electrons, and you are calculating for S or P electron, right? That time same shell 0.35 I have mentioned. Come back to this. Here same shell, if it is there, 0.35 I said. So go for this back. Next, here inner shell n minus 1 What is n minus 1 shell? What is that? 1s orbital, right? In that, how many electrons are there? 2 electrons are there. Yes, 2 electrons are there. And you are calculating for s electron. S electron n minus 1. What is the what? S value for n minus 1 electron? 0.85. That's why there are 2 electrons. So 2 into 0.85, write it. So what is this? 0 plus 1.7. So S value is what? 1.7. That 1.7 you have to subtract it from 3. How much it is? 1.3. So what is the meaning of this 1.3 is, see this valency electron, whatever the valency electron is there, let me turn it. Look at this. This valency electron, whatever the valency electron is there are 3 electrons, right? Yes, this valency electron is expected to have 3 protons attraction, but in reality is what? 1.3 protons attraction only. What about remaining 1.7? That attraction is minimized, shielded or screened by inner electrons. What are they? 1s electrons. 1s electrons are protecting the 2s electron from the nuclear attraction. That can be calculated excellent with the help of Slater's rule. Are you clear, my dear? Yes. We will see one more example, then you'll get the clarity. If you wanted, you can go back, right? Replay it, you'll get it. And we go for the another example. See, another excellent model. What is that? Sodium. Sodium. What is sodium electronic configuration? First write down. Sodium electronic configuration. Sodium atomic number 11. Write down the electronic configuration. 1s2, 2s2, 2p6 and 3s1. Now what I told you, after writing the electronic configuration, you need to regroup it. What is that? 1, 2 and 3. So third shell, what is this? N. This is what? N minus 1. First shell is what? N minus 2. And you are calculating a valency electron of sodium, 3s electron. S and P, what I told you? S and P, this order we need to follow. Now write down effective nuclear charge is equals to atomic number minus screening constant. How to calculate it? With the help of Slater's rule. Yes. What is S for this? Valence electron of sodium. Can you calculate it? This is N. Is there any other electrons? Look at this. Here one valence electron is there. Is there any other electron? This one you need to indicate what? Number of electrons present in that particular shell. One electron, only one electron. For that electron only you are calculating. Obviously, there is nothing required here. So, inner 8 electrons, n minus 1, 8 electrons are there. In n minus 2 shell, there are 2 electrons. Come back to this. So, 0.35 into 0.35 plus n minus 1 shell. How many electrons are there? N minus 1 shell. 2 plus 6, 8 electrons are there. You are calculating for s electron. That's why 8 into 0.85 because you are calculating for SRP electron. If it is DRF electron, you would have taken 8 into 1. Clear, right? Yes. Next, n minus 2 shell. How many electrons are there? 2 electrons are there. N minus 2. 2 electrons. Come back to this. N minus 2. What is that? 1 we have to take it. Screening constant is 1. So 2 into 1. Now this is what? 0 plus 6 point. Yes, I think 2 here. So 8.8. If I'm not wrong, verify that. And atomic number 11 minus 8.8. 8.8, right? So what is the value? 2.2. Correct, right? Yeah, 10 plus 2, 10 plus 1, 11. Yes, look at this. How how much the nuclear charge is decreased? We expected how much? We expected 11. Reality is what? 2.2. That means what? 8.8 is decreased. 8.8 is decreased in the sense what is the meaning of this one? Tell me. Yes. So this valency electron, whatever the valency electron is there, this valence electron is there, right? Yes. This valence electron is expected to have 11 protons attraction, but it has 2.2 protons attraction. Simple logic. When attractions are decreased, size increases. Am I right or wrong? Yes. Slater's rule, how effectively is calculating? Look at this. See, this proton is expected to have 11 protons attraction, but reality is what? 2.2 protons attraction. That means what? The centripetal force is less than the expected. Obviously, electron will go away. The valence electron will go away. When an electron is going away, then obviously what happens? The distance between nucleus and valence electron increases. Distance between nucleus and valence electron is nothing but what? Atomic radius, size of the atom, boss. That's why size increases. Clear, right? Next we go for next atom. What is this? Zinc. Very good. So this is very popular question. It is actually. So let us come back to this zinc. So as I told you, now without seeing the board, try to write very quick. So first write down the electronic configuration. To answer this, you should know atomic number, right? Tell me what is the atomic number? Don't look for the periodic table. Zinc is very popular, right? 30. What is the electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s2. Yes, why I am writing like that? See, as I told you, right? Grouping, we have to do it in such a way that, yes, the valence electrons are away from the nucleus. Yes, you do the grouping. Yes. Here, try to remember, whenever you are calculating 3D, that time only subgrouping we do it. Otherwise, these three subshells are considered as what? Belongs to one energy level. Okay, now what is this? This is nth shell, n minus 1, n minus 2, this is n minus 3. Is this clear? So, n minus 1, n minus 2, and n minus 3. Yes, now I wanted to calculate it for 4s electron. How to calculate it for 4s electron? Let us see. Effective nuclear charge, as usual, is equals to 30 minus S. S we need to calculate it. S is equals to, yes, here, this is what? Outermost electron. I wanted to calculate it for that. Look at here. This electron, I wanted to calculate it. There is another electron also. Why? Two electrons are there in the valence shell. One electron is there. So this is my interest. So what about the other electron? Definitely in the process of but revolving, it may come, right. So we are not saying that it is revolving in a circular orbit. Yes, in the process of moving, so the other electron may come in between nucleus and outermost electron. It can protect some extent. What is the value? 0.35, right? Yes, that we take it. So apart from the interested what area of interest, the other electron is what? 1. So 1 into 0.35. Next, n minus 1 shell. How many electrons are there? This is S. That's why n minus 1 means, so n minus 1 electron, each electron 0.85, right? See, what is that? S constant value is what? 0.85. There are how many electrons? There are 18 electrons. 18 into 0.85 plus here remaining n minus 2, n minus 3, what I said? N minus 2, n minus 3, it is 1. N minus 1, 0.85, right? Yes, come back to this. So how many electrons are there? 6 plus 2, 8 plus 2, 10. 10 into each electron contributes 1. So that's why 10 into 1. Yes. So 1 into 0.35, 0.35, 0.6 plus 10. Clear, right? Yes. So how much it is? 18.6. 18.6 plus 0.35. 18.95. Am I right? 18.95. That you subtract from 30. So 11.05. Am I right? Yes, 11.05. Look at that. We expected 30 protons attraction on the valence electron, but reality is what? 11 protons attraction. Why? Why that decreased? Because there are many electrons in n minus 1, n minus 2, even n minus 3 shell also. That's why there are more electrons inside. Their protecting power is different. That's why the net attractions experienced by this valence electron is less than, very less than the expected. Where is 30? Where is 11? That's why size increases. Let us say we have calculated for 4s electron, same zinc atom, but if you wanted to calculate for 3d or 3p or 2s 2p or 1s electron, then how to calculate it? Let us see. Earlier this is valence electron, now it is no longer valence electron. We no, valence electron only, but it is not required for us. Why? I'll tell you. And this grouping will change. As I told you, whenever you are calculating for 3D, definitely you need to regroup it, because 3D is what? Away from the nucleus. Try to understand. As I told you, 2s and 2p or 3s 3p, s or p electrons in simple way, they are close to the nucleus because of their shape, orientation of the orbital and shape of the orbital. The s and p electrons are available close to the nucleus. D and f are what? Available little away from the nucleus. Just imagine 3s 3p is here, 3d is here. 3s 3p because of what? A shape of the orbital they are, we expected like this, but because of the shape of the orbital that is close to the nucleus, this is away from the nucleus. So nucleus is inside. 3s 3p, 3s 3p, 3d and 4s. You understand what I'm saying? Within the same energy level only, but 3s 3p is close to the nucleus, 3d is away from the nucleus. Is this clear? That's why regrouping we need to do it. And now 3d is nth shell, 3s 3p is n minus 1 energy level, and this is n minus 2, and this will be n minus 3. This is of no use. Why? Let us see. Here I wanted this electron, any that 3s 3p or 3d electron is here, but a 4s electron is here. So what shielding or screening effect? The net attraction forces experienced by the outer electron from the nucleus, I said. That is what? Effective nuclear charge. So when inner electrons are coming in between outer electron and nucleus, then only they can protect, I told you. This 4s electron is away from the nucleus. How this 4s electron can protect a 3s 3p or 3d electron which is inside? Clear, right? That's why screening effect, shielding effect for 4s electron on 3d is 0. We don't consider. Okay. Now effective nuclear charge is equals to Z atomic number minus screening constant. So now you calculate it. What is that? S is equals to, what is the value? There are 10 electrons in n level, nth shell or n level. So 1 electron is our interest. Remaining 9 electrons are there. That's why 9 into 0.35 plus, this is what? N minus 1. N minus 1. But the problem is what? You are calculating for D. Look at this. Forget about this. Now you are calculating for DRF electron, right? Yes, this you have to consider. What is this? Nth shell 0.35 or n energy level 0.35, n minus 1, 1, n minus 2, n minus 3, n minus 4. Anything is there, we have to take it as 1. Come back to this original discussion. So this is nth level, this is n minus 1, n minus 2, n minus 3. Only nth levels 0.35 into number of electrons, remaining all the electrons into 1. Yes, how many are there? 8, 8 and 8. How many? 18. 18 into 1. Yes. How much? 4.15 plus 18, 22.15. Right? So now you calculate it 30 minus 22.15. How much? So 7.85. Look at that. We expected how much? We expected 30 protons attraction, but reality is what? 7.85 protons attraction. That effective nuclear charge decreased. Clear, right? Yes. I told you, regroup it. And now this is n, this is n minus 1, this is n minus 2. As now you calculated effective nuclear charge is equals to atomic number minus screening constant. Screening constant for nth level. Look at this. There are 8 electrons. 1 is our interest. Remaining 7 electrons are there. 7 into 0.35. And now you are calculating for SRP electron. That's why n minus 1, 8 electrons into 0.85, not 1. It is not D or F electron. And this one is what? N minus 2. There are 2 electrons into 1. Okay. Calculate it and keep the value in this. 2.45. 6.80 plus 2. So 8.10.8, 11.25. So correct me if I'm wrong. 30 minus 11.25. How much? So 18.75, is that right? That's it. Look at that. That 3s or 3p electrons are experiencing how much? 18 proton, more than 18 protons attraction instead of 30 attractions. So can't you able to calculate it? The similar. Now you calculate for 2s, 2p and 1s also. So what is the formula? As usual, effective nuclear charge is equals to Z minus S. S is equals to, there are 8 electrons, so 1 is our interest, remaining 7 into 0.35 plus inner n minus 1. So you are calculating for SRP electrons, that's why there are 2 electrons into 0.85. So 35, 2.45, and this is 1.7. How much? 4.15, and now 30 minus 4.15. How much? So 25.85. Look at this. When you are coming close to the nucleus, effective nuclear charge is changing. Now you calculate it for other one. Same way you calculate it for 1s electron also. 1s electron, for 1s electron in zinc. How to calculate it? Zinc atomic number 30, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. This is zinc. My interest is this N. These are all what? Nonsense. They cannot protect the 1s electron from the nuclear attraction. Yes, now you calculate for N for 1s electron. Sorry, now you calculate S for 1s electron. As usual, effective nuclear charge is equal to atomic number minus S. So what is S? As I told you, one exemption I told you, generally same shell electron protecting power is what, 0.35. Yes, so if this is my interest, so obviously the other electron, generally what happens, 0.35 will be there for screening constant, 0.35 will be there, but 1s electron, if it is 1s electron, the screening constant is 0.35. Directly you take as S is equals to 1 into 0.35, you need to do it, 0.35 you'll get it. That 0.35 you subtract it from, not 0.35, 0.3, that you subtract it from 30. So obviously 29.7 you'll get it. Clear, right? This is the way you need to calculate Slater's rule, right? You need to calculate effective nuclear charge by using Slater's rule. Simple, easy, but you need to have some patience. Try to understand step by step, you'll get the clarity. Yes, without wasting time, I'll revise quickly. And before going to that, I wanted to give you some questions. So please note down. Scandium is that. Calculate the effective nuclear charge present in the valency shell electron, that is what, scandium valency electron, 4s electron. What is the scandium atomic number? 21. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2. For this electron, 4s electron, you calculate it. Even you can calculate for calcium also. Calcium atomic number 20, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 for this valence electronic calculator. Clear, right? Yes. So just we will go quickly to the total discussion one more time. See, let us see one by one what is Slater's rule and everything we'll see. What is Slater's rule? Yes, Slater's rule is a tool. It is a simple technique to calculate the effective nuclear charge experienced by the valence electron. Yes, what is effective nuclear charge? The net attraction forces experienced by the valence electron from the nucleus is called effective nuclear charge. Why the net attraction forces are decreasing? Because when inner electrons are coming in between outer electron and nucleus, the inner electrons will push the outer electron from the nuclear attraction. These electrons will push the outer electron away from the nucleus. They act as a screen, shield, protective shield, right? That's why shielding effect we say. Different elements will have different electrons will have different shielding capacity, screening capacity. Generally, S or P electron will have more shielding effect than D or F electrons. Yes. What is the formula? Slater's rule. According to Slater's rule, effective nuclear charge is equals to atomic number minus screening constant. So we need to calculate the screening constant S value for a particular electron, and you subtract that value from the atomic number of the element, then you'll get the effective nuclear charge. Right? Yes. So here, as I told you, S electrons will protect more than D. SP will have more protecting power capacity than D and F, I said. The reason is what? S electrons or P electrons availability is more around the nucleus, more concentrated, more protecting, more shielding capacity than D and F electrons. Because D and F electrons are what? More lobes are there, more distributed, more area they are covering. That's why more distributed, more diffused, they cannot protect the outer electron from the nuclear attraction than S and P. That's why, yes, S and P will have similar energy. That's why, according to the Slater's rule, we need to regroup the orbitals like this: 1s, 2s2p, 3s3p, 3d, 4s4p, 4d, and 4f, like that. We need to regroup them in increasing order of energies, or the what? Slater constant base. So now effective nuclear charge. How to calculate? Let us see this. See, for example, this is the same shell, same energy level, same group, I can say. This is n minus 1 and this is n minus 2, this is n minus 3 shell. Okay, if any electron is present in the same energy level, the other electron can have some shielding constants that can protect the electron. See, for example, here one electron is there, another electron is there. In the process of revolving, so it may come in between nucleus and outermost electron. They can protect. So that time screening constant is what, 0.35. And one exemption is there. If the other electron is 1s electron, that means what, here 1s electron, that time 0.3 will be there, generally 0.35. Yes, for SRP electrons this is the order, DRF electrons this is the order. So n minus 1 shell only the different. Here for SRP electrons, the n minus 1 electron screening constant is what, 0.85. For D or F electrons, n minus 1 electron screening constant is 1. Remaining all the electrons, what, n minus 2 or n minus 3 electron, whether you are calculating for SRP or DRF electrons, the screening constant value is 1. Yes, by keeping all these rules, we can calculate the screening constant and effective nuclear charge for a particular atom and that to a particular electron. Let us see lithium atom. What is the lithium atom? Oh, the atomic number is 3. There are 2 shells, first shell and second shell. So first shell 2 electrons are there, second shell one more electron is there. Yes, this is called valence electron because it is valence shell, outermost shell, ultimate shell. Yes, this you wanted to calculate it. That time the same thing, formula is what, effective nuclear charge is what, atomic number and atomic number minus screening constant. What is screening constant for this valence electron? You wanted to calculate valence electrons, effective nuclear charge on valence electron. Yes, this you take it as what, n, and obviously this is n minus 1 shell. Yes, for nth shell. Apart from this, there is no other electron. Only one electron is there. So there is no other electron to protect, which is present in the same shell. That's why 0 into 0.35 plus there are 2 electrons in the n minus 1 shell. But you are calculating for s electron, right? That's why we need to follow this order, not this. Okay? Yes. And there are 2 n minus 1 electrons, so 2 into 0.85, so you'll get 1.7. So overall effective nuclear charge is what, 3 is the atomic number, minus 1.7, 1.3. What is the meaning of this one is, this outer electron is expected to have 3 protons attraction, but it is experiencing 1.3 protons attraction only. That means the inner electrons are protecting this much nuclear attraction from the nucleus. Clear, right? Yes. Next one, sodium. If you calculate for sodium, what is the electronic configuration? 1s to 2s to 2, p6, 3s1. Yes, now you calculate for 3s electron. 3s electron, how to calculate it? Yes, this is the valence shell, n, n minus 1, n minus 2, like that you regroup it based on Slater's rule. So apart from 3s, there is no other electron. That's why 0 into 0.35 as usual, like earlier. And here n minus 1 shell, how many electrons are there? There are 8 electrons. 8 into 0.85 plus n minus 2, how many electrons are there? 2 electrons are there. 2 into 1. So add all that, 8.8 you'll get it. 8.8 you subtract from 11, you get 2.2. That means the valency electron of sodium is experiencing 2.2 proton attraction instead of 11 protons attraction. So that is the meaning. And yes, for zinc atom you can calculate it. So again you regroup it. So whenever you are calculating 3D, that time only you group it again, regroup it as 3p together, 3D separately. Otherwise normal only. So for this electron, this is nth shell, n minus 1, n minus 2, n minus 3 energy level kind of. So apart from our electron, one more electron is there. That's why 1 into 0.35, and n minus 1 level, 18 electrons are there. That's why 18 into 0.85. And here how many are there? 8 plus 2, 10 electrons. So that's why 10 into 1, and add it, 18.95 you'll get it. That is subtract from 30, you'll get 11.05. So like that, see this here is important. Whenever you are calculating for 3D electron, the 4s electron is what? Valence electron. That 4s electron is what here? 3d electron is here, 4s electron is here. How outer electron can protect inner electron from the nucleus? Right? That's why 4s electron we don't consider. So leave it. And our interest is what 3d. That's why you take it as n. 3s 3p n minus 1, 2s 2p n minus 2, and 1s2 is what n minus 3. So you calculate it and get the answer. The same way 3s electron also, 3s 3p also, 2s 2p also, you can do it. Clear, right? These are the values. This is 1s electron. So 1s electron, this is important actually. Whenever 1s electron is there, generally same shell electron screening constant value is what 0.35, but for 1s electron the screening constant value is what 0.3. That you remember. Any element, not only zinc, any element 1s electron screening constant is what 0.35. So, sorry, 0.3. 1 into 0.3. So 30 minus 0.3, 29.7. Is this clear, my dear? Yes. Even I have given some question also. Two questions I have asked you. One is calculate the effective nuclear charge experienced by valence electron of scandium as well as calcium. You can do it like for 3D also 3p, 3s or 2s, 2p or 1s electron. You can calculate it without any confusion. I hope you understood, right? Yes, this is very easy. Need some experience. You need some clarity. Yes. Any doubt you have, please write your message in the comment box. I will be reading your message. Definitely me or my team members will reply to you. Thank you very much for your love and support. All the very best for learning, right? All the best. Thank you very much.